Hi everybody and welcome back. This is example 11.5, well actually it's 11.6. I should change that. We've got our numbering off a little bit. This is 11.6 and we're going to be dealing with a car going around a corner again. But you can see right here that there's going to be a couple more parts to it, but that's okay. We'll take them in stride and do one at a time. So we have a car with a mass of 1,300 kilograms. All right, so that's good to know. 1,300 kilograms, and it goes around a corner with a radius of 59 meters. All right, so radius equals 59 meters, and with a speed of 16 meters per second. Now I'm going to call that V for velocity, or really instantaneous velocity. At any one point, I should say, but of course the velocity isn't constant because the direction keeps changing. And we also have the mass of the dice. All right, so mass of the dice equals 110 grams, which if we convert that to kilograms, that's 0.11 kilograms. Okay, that's good to know. Now, your rear view mirror has fuzzy dice hanging from them, and if you've never seen them, you're probably better off. But these were kind of a car fad back in the 70s and 80s, but you would have your rear view mirror right here, and then dangling from it were these kind of dopey looking plush fuzzy dice. Or honestly, it could be anything right now. It could be a graduation tassel or any kind of other little thing hanging from your mirror. But at any rate, they normally hang straight down because of gravity. But in this case, they're going to be kind of off to the side because your car is going around a curve. All right. So what we want to find here. Let's take a look at our questions. First of all, we want to find the force exerted on the car by static friction. All right. Well, the car is going around a curve, and the only thing keeping it in that curve is static friction between the tires and the road. So that's going to be important. Part B: calculate the angle that your dice make with the vertical. So this angle right here with the vertical is what we want to calculate. Thirdly, we want to find the tension in the string holding up the dice. All right, we're going to assume the string to have no mass, but only the dice have mass, and we're going to compare the angle of your keys, which have more mass than your dice. We're going to compare that angle to the angle of the dice. All right. So, all that being said, let's go ahead and shrink this down here. Put that up in the corner. All right. First thing we want to do is we want to draw a free body diagram of our car. You don't have to be an artist. This is going to be for part A right here. You don't have to be an artist, but you do need to represent your object that's going around in the curve, around the circle. So I'm going to draw it kind of like that, coming at us, and got our black tires right here. And the curve is sort of sweeping around that way. All right, so the car is gonna kind of have this motion like that. In fact, I probably shouldn't have done that. Oh, I'm messing it all up. Bugger. Tires, road, and the road is sweeping like that. Okay, so what's keeping? And again, the car is coming at us right here. What's keeping the car on that curved path? Well, the centripetal force, right? But that force is not being provided by any kind of string or rope or wall or anything. It's simply being provided by the friction or the static friction between the tires and the road. And that's it. And you know that if that friction goes away, like if somebody sprays grease on the road or something like that, you're no longer going to be able to maintain that path and that curve, and you go sliding off the road. So what we can say here is that the static friction force equals the net centripetal force. It's the only centripetal force that's keeping the car on the road right there. That's helpful because if we say the net centripetal force equals the static friction force, we can always state the net centripetal force in another way too. That is, net centripetal force equals mass times the centripetal acceleration. Sound familiar? It should. So we're applying the same Newton's law principles and kind of step-by-step methods that we did before, but this is simply going to be in circular motion. So both of these things being equal, let's set them equal to each other. Static friction force equals mass times the centripetal acceleration. Now, in most cases, we would try to find the static friction force by taking the coefficient of friction times the normal force, which is mg, but we don't have to do that here. We can find it because all the question is asking us is, what is the static friction force between the tires and the road? Well, we have these values here, which we can set equal to static friction force and find it that way. So what's the mass of the car? The mass is 1,300 kilograms. All right? And what is our centripetal acceleration? Well, let's look and see what we have here. We have radius and we have velocity right here. I think we can state centripetal acceleration. You know what? I wanted to go back and, well, that's all right. Centripetal acceleration is v squared over r, right? See, I was too fast to... Here, I'll just do this. Put a big M right here. We're still keeping this a general equation. M times our centripetal acceleration is v squared over r. All right? So we'll plug our values in for that and then get an answer for our static friction force. So that is 1,300 kilograms, sorry. 1,300 kilograms times the velocity squared. What's that? 16 meters per second. That value squared. All over the radius of 59 meters. Okay? Static friction force. This is the force that is directed sideways from the car towards the center of it. So 1,300 times 16 squared divided by 59, I get 5,640. Well, I'm going to round it up to 41. 5,641 newtons. All right, so that is a force that is being applied towards the center of this curve in order to keep the car on the road. All right, that's our static friction force, and that's the answer to part A. Okay, part B. Part B, and I hope I have enough space here. Here it's asking us what the angle that your fuzzy dice in your rear view mirror make with the vertical. All right, now I'm going to just go ahead and draw a little free body diagram right here. Like so. And in fact, you know what? That's too close to the side. There we go. All right, there's your rear view mirror. And normally, the dice hang straight down. Why do they hang straight down? Because of gravity. But, in fact, I'll draw them in blue right here, all right? Straight down, and instead of dice, I'm just going to make a ball just because it's easier than drawing two little cubes right there. All right, but at this particular point in time, they're kind of hanging at an angle right here. At an angle because we're going around a corner. Okay? So, right here is really what it's... what's happening to it, and what we want to find is what this angle is from the vertical right there. All right, so let's turn this into a force triangle. All right, we have a couple different forces acting together to cause this fuzzy dice to hang at this angle. First of all, let's ask ourselves, what is the force acting in the vertical direction? Well, this is the force that's always acting in the vertical direction, whether the car is going around a corner or not. And that is the supporting force to keep it up, that is the normal force, or mg, right? Even at rest, the string has to be applying a force up to counteract mg. Mg is acting downward, so you could probably call this the normal or upward force. All right, but that's what's happening in the string right there. That's vertically. That's the same thing as mg. But it's also true that there is a horizontal component as well. All right. By the way, the mass we're talking about is the mass of the dice. All right, the mass of the dice, not of the car, but of the dice. There's a horizontal component. That horizontal component is the mass of the dice times the centripetal acceleration, right? Because the centripetal acceleration that the car is experiencing, that v squared over r, the dice are also feeling as well. All right, and so the die wants to fling out this way because the car is accelerating it towards the center of that curve right there. All right, so we have this kind of vector triangle of forces. So, let's see if we can clean this up a little bit here. If this is mass times centripetal acceleration, and that is our normal force, which really is equal and opposite to mg, we should pretty easily be able to find what this angle is right there, because we have an opposite and we have an adjacent. All right, what is our mg? Our weight force, the force that's always acting on it, whether the car is curving around a curve or not. Normal force equals mg, which equals, what's the mass of those fuzzy dice? 0.11 kilograms times 9.81 meters per second squared. I'll calculate that in just a second. And our mass times the centripetal acceleration, that is 0.11 kilograms, times the centripetal acceleration. Well, we got that from v squared over r, right? So the velocity squared is 16, I'll just leave the units out for now, 16 squared over 59 meters. That's going to be our centripetal acceleration. All right, so let's find out what that is. Our normal force, 0.11 times 9.81. I should have been able to do that. No, not necessarily. All right. Thought I could have done that in my head, but it's a little messy. 1.008 newtons. So that's the force that is acting vertically right here. Let's find the force that's acting horizontally on these fuzzy dice. 0.11. I put an extra 1 there, didn't I? That should be a 0. 0.110 kilograms times 16 squared divided by 59. That's 0.48 newtons. Okay, so that means if we want to solve for this angle right here, this angle theta, we have an opposite, that's 0.48. We have an adjacent, that's a 1.08. So we should be able to say that the angle theta, I'll do that in green, theta is, well, actually, let me back up. What sine function should we use with opposite and adjacent? That's tangent, right? So the tangent of theta is going to be equal to opposite, so that's 0.48, the opposite over the adjacent, which means that theta itself is the inverse tangent of that fraction right there, 0.48 divided by 1.08. All right, we see how we got that? We turned this angle into a force vector triangle, and so we're solving for this angle right here using the opposite and the adjacent. All right, so what should that angle be? What's the inverse tangent of 0.48 divided by 1.08? Oops, that's not right. Delete. 23.9 equals 23.9 degrees. From the vertical, that's what that angle is right there. Okay? All right. Now that seemed like a little bit clumsy, or it may have to you. Or if nothing else, maybe it just seemed like a lot of work, but what this means is that we made our lives a lot easier for this next part. All right, so the part C is asking us, part C, what is the tension in the string? It's really saying, what is that tension right there? Because that's really the direction that the string is hanging at, because these dice are flinging out to the side right there. What is the tension in the string? Tension being a force. Well, the two forces that are acting on these dice are the force we found down here, the 0.48 newtons and the 1.08 newtons. So all we needed to do is use our Pythagorean's theory, 0.48, and this is 1.08, and find out what that hypotenuse is. Should be pretty easy. That is, I'll write that in black. That's going to be our tension force in the string. All right, so 0.48 squared plus 1.08 squared. Take that to the 1/2 power, the square root, that is 10. The tension force is 10.8. Newtons, and that seems really high. What did I do there? Oh, I know what I did. I changed some of the numbers around there. All right. I plugged in 10.8 instead of 1.08, so I moved the decimal point over. So that's not right. I can't erase that, but that's okay. 1.08 squared plus 0.48 squared, square root. I get, this sounds much better, 1.18 newtons. And that makes a lot more sense because we've got these little lightweight fuzzy dice. Okay, so that's how much tension is in the string being directed up the string towards the top where the rear view mirror is. All right, lastly, D, and keep changing colors again. D, let's say we have something that is heavier or more massive. All right. Well, this is sort of a conceptual thing, so we're not going to do any calculations right here. But if you have something that's more massive, like say your keys, all right, your keys are made of metal, they have more mass than these fuzzy dice things. What's likely to happen? Well, this mg force right here, the mass of the object, in this case your keys, times gravity, is going to be much greater, right? You're going to have a much greater mass of the keys times gravity. And yet the keys are still experiencing the same centripetal acceleration. In this direction right here. Mass of the keys times centripetal acceleration. Okay, so you say, all right, well, you've got a greater mass here in the keys. What's going to happen to this angle? This angle at which they hang from the vertical. All right, well, look. This mass and this mass are the same, all right? This mass, and now we're back to talking about the dice, this mass and this mass are the same right here. Basically, it could be any masses, and it wouldn't matter. They're all going to hang at the same angle. All at the same angle because it's basically the same proportions. Hey, if you factor out the masses in the vertical and the horizontal and the hypotenuse right here, you have the same proportions. You have the centripetal acceleration is the horizontal component, and gravity, g, is the vertical component right here. So that would make the hypotenuse the same. So it should mean that this angle right here is going to be the same. Same as the previous one, and that's 23.9 degrees. Okay, so that's example 11.6. And if you have any questions about that, please make sure you come see me. Thanks for following along. I'll see you on the next one.